Welcome to my poster presentation. The goal of our work is to build a deep neural network which is less artificial than nowadays standard deep neural networks, which means without any derivatives of backpropagation inside. We focus on the visual cortex as the best investigated part of the neocortex and aim to be able to solve realistic tasks such as invariant object recognition, and we want to gain insights into receptive field properties by advancing the knowledge in the area V2. And finally, we want to observe the anatomical footprint of the learnings and link here the observed connectivity of the inhibitory neurons to its functioning, explaining why their connectivity is often described as unspecific despite the learning is indeed specific. To do that, we had to combine three core principles which together enable these insights: synaptic, intrinsic, and structural plasticity. First, synaptic plasticity, to learn informative representations on the neuron level, where excitatory plasticity extracts correlating patterns from the input, and inhibitory plasticity causes response decorrelation by penalizing coactivity. We use plasticity formulations where the weight strength develop relative to the correlation of the pre- and postsynaptic activity. These rules have been demonstrated in earlier work to learn proper V1 simple and complex cell receptive fields. Second, intrinsic plasticity. The decorrelation of the neurons through inhibition does not ensure that all information present in the input is also represented by a population of neurons. A further issue of the formulation of Hebbian learning is that synapses from more active neurons are more strengthened and can dominate the neural code. These imbalances in the representation of different patterns can harm the neural code in downstream layers. This can be resolved by aiming for equal mean and variance of the neurons. Here an example from the second layer of our model. With intrinsic plasticity, the mean activity of all neurons is in a narrow range, and all neurons are doing something. Whereas without intrinsic plasticity, a lot of neurons are doing nothing, while a few neurons dominate the neural code. And third, structural plasticity. It is difficult to decide on the individual connectivity. With structural plasticity, we can find the individual connectivity during learning of the receptive field. This also allows us to observe the anatomical footprint of the learning. Let's have a look at the model to get a clue how structural plasticity can be beneficial. We have 9 populations of recurrently connected neurons. These are about some thousand neurons and about 1 million synapses. For the initial connectivity, we use theoretical assumptions on the organization. Each neuron has a limited window of connected neurons, and the connections of the neurons are retinotop organized. On population and layer level, the connectome was designed to follow findings on the neocortical connectivity. However, we do not know the right connectivity of, for example, 2 neurons from these populations here. Therefore, we will find during learning the connectivity structure with a mechanism we call experience-dependent structural plasticity. We base this mechanism on 2 basic neuroscientific findings. The formation of new synapses is more likely in the neighborhood of other strong synapses. We know the neighborhood because of our initial retinotop organization. And second, weak synapses are more likely to be removed. The result is that receptive fields grow and shrink in their spatial surrounding. And experience, which determines the weight strength, is the important factor which determines the connectivity. Let's jump over the object recognition results and have a short look on the receptive fields. We have shown in earlier studies that our approach produces V1 simple and complex cell receptive fields. Thus, we look here for the properties of the poorly understood V2 neurons. A neurotheory says that they are more sensitive to naturalistic textures than to spectral matched noise, whereas V1 neurons don't care. We also found this trend in our model, and we could advance what is known from experimental data by a fine-grained analysis for layers and neuron types. Finally, we analyzed the learned connectome in our model. While excitatory neurons show a clear trend that neurons which share a higher response correlation also are more likely to be connected. We observed a different pattern for inhibitory neurons. Uncorrelated neurons have a connection probability slightly below chance level, whereas negatively and positively correlated neurons are slightly above. However, the connection probability drops for highly correlating neurons. This is the case because of the function of inhibition to decorrelate the neurons. Only unconnected neurons can develop high correlations. When they are connected, then the correlation quickly decreases because of the increasing inhibitory weight. After a short time, these neurons are uncorrelated or slightly negatively correlated, and the weight decreases. Weak synaptic weights are likely to be removed. However, structural plasticity is slow and neurons end up with a pool of seemingly unspecific synapses, despite inhibition acts highly specific. This is difficult to discover in experimental studies, as these strongly correlated neurons are rare and exist just in relatively short time windows. So experiments will just observe the statistics of uncorrelated and slightly correlated neurons. Finally, let's shortly mention the two main challenges we have for computational modeling the neocortex. Excitatory recurrence, which causes instability, and task-specific learning via cortical feedback. Thank you for your attention, and I'm looking forward to the live session.